Section 3.2, norm, dot product, and distance in Rn. If v equals v1, v2 through vn is a vector in Rn, then the norm of v, also called the length of v or the magnitude of v, is denoted by this symbol over here and is defined by the formula square root of v1 squared plus v2 squared and so on all the way through vn squared. So we basically just take each of the entries and we square them and then take the square root of the sum. Let's find the norm of the vector v equals -3, 2, 1 in R3 and the norm of the vector v equals 2, -1, 3, -5 in R4. So first we will take -3, square it, add that to 2, square it, add that to 1, and square it for the first vector v, and we'll take the square root of all of that sum. So that's the square root of 14, and that's just square root of 14. So that's for v equals -3, 2, 1. Okay, how about the other vector v? I'll take 2 and square it. I'll add that to -1 and square it. Add that to 3 and square it, and add that to -5 squared, and take the square root. Okay, and that's square root of 39. For v equals 2 minus 1, 3 minus 5. If v is a vector in Rn, and if k is any scalar, then we have that the length of v, magnitude of v, is always greater than or equal to 0. The length of v equals 0 if and only if it's v is the 0 vector. And a scalar times v, when we take the length, is just the absolute value of the scalar times the length of v. So the scalars can be pulled out of lengths. A vector of norm 1 is called a unit vector. If v is any non-zero vector in Rn, then the unit vector u is 1 over the length of v times v. So basically we just take v and divide it by its length. That'll define a unit vector in the same direction as v. The process of multiplying a non-zero vector by the reciprocal of its length, basically this process, to obtain a unit vector is called normalizing v. As an example, let's find the unit vector u that has the same direction as v equals 2, 2, minus 1. So first we'll find the length. Don't like that line came out. That's better. And that's going to be 2 squared plus 2 squared plus -1 squared. Just squared each of its components and add them together, and you should get 3. So that means that the unit vector u in the same direction as v is 1 divided by 3, because 1 divided by the length, times the vector v, 2, 2, minus 1. So multiplying by 1/3, that becomes 2/3, 2/3, minus 1/3. When a rectangular coordinate system is introduced in R2 or R3, the unit vectors in the positive directions of the coordinate axes are called the standard unit vectors. In R2, these vectors are denoted by I equals 1, 0 and j equals 0, 1. In R3, they're denoted by I equals 1, 0, 0, j equals 0, 1, 0, and k equals 0, 0, 1. Every vector v equals v1, v2 in R2, and every vector v equals v1, v2, v3 in R3 can be expressed as a linear combination of standard unit vectors by writing v equals v1, v2 is whatever the component v1 is times that I vector, 1, 0, and that's just v1i, and then you do the same thing for v2, multiply it by 0, 1, that's j. You do the same thing for R3. And you can generalize these formulas to Rn by defining the standard unit vectors in Rn to be e1, e2 through en, where you just take a 1 and you put it in whichever slot the subscript denotes. So that means that every vector v in Rn can be expressed as some linear combination of these guys, e1, e2 through en, etc. Shouldn't be super surprising because imagine there's a constant here. You multiply it by 1 and then 0 for all the other ones, so then you get a constant in that first entry, etc. As an example, how about we write the vectors 2, minus 3, 4, and 7, 3, minus 4, 5 as linear combinations of standard unit vectors. So first we'll start with 2, minus 3, 4. And we'll just have to take 2 times this first one. So we'll take 2 times 1, 0, 0, which is I. And then we'll subtract 3 times 0, 1, 0, which is j. Multiplying by the 1 will keep the minus 3, and the zeros would kill off the other ones. And then we will add 4 times k, which is 0, 0, 1. We'll do the same thing for 7, 3, minus 4, 5. And we'll get 7 times e1 plus 3 times e2 minus 4 times e3 plus 5 times e4. If u equals u1, u2 through un, and v equals v1, v2 through vn are points in Rn, then we denote the distance between u and v by d of uv, and we define it to be the length of the vector u minus v. So that's the square root of u1 minus v1 squared, u2 minus v2 squared, and so on. Let's calculate a length real quick. This should be pretty familiar. It's just the Pythagorean theorem, basically. So we'll take d of uv equals, let's see, we're going to take u1 minus v1. So that's 1 minus 0. And we'll square that, and we'll add that to 3 minus 7 squared, and we'll add that to negative 2 minus 2 squared, and add that to 7 minus 2 squared. Just take each of these and just subtract the corresponding component. So we will take the square root of all of that, and you should get the square root of 58. Let u and v be non-zero vectors in R2 or R3 that have been positioned so that their initial points coincide. We define the angle between u and v to be the angle theta determined by u and v that satisfies the inequalities theta goes from 0 to pi. So if u and v are non-zero vectors in R2 or R3, and if theta is the angle between u and v, then the dot product, also called the Euclidean inner product of u and v, is denoted by u dot v, and is defined as the length of u times the length of v times the cosine of the angle in between u and v. If u equals 0 or v equals 0, then we define the dot product to be 0. As an example, how about we find the dot product of the vectors shown in the figure? So let's see. We need to find the length of u. So that's the square root of 0 squared plus 0 squared plus 1 squared. So the square root of 1 squared is just 1. So the length of u is 1. Now we need the length of v. That's 2 squared plus 2 squared is 4 plus 4 is 8. So it's the square root of 8, which is 2 radical 2. The angle between them is 45 degrees, so we'll get the cosine of 45 degrees, and that equals 1 over the square root of 2, or rad 2 over 2 if you prefer. Either way, we get that the dot product is equal to length of u times the length of v times the cosine of the angle between them, theta, and that's 1 times 2 rad 2 times 1 over rad 2. So the rad 2's cancel, and I just get 2. So that's the dot product. If u equals u1 through un and v equals v1 through vn are vectors in Rn, then the dot product, also called the Euclidean inner product of u and v, is denoted by u dot v and is also defined this way. So these definitions are actually equivalent. We can compute the dot product either by taking the length of u, length of v, and the cosine of the angle between them, which can be convenient if we want information about the angle between them, or we can compute them just by multiplying corresponding components together. So let's use this alternative definition to compute the dot product of the vectors u and v in example 5. So notice I'll take u dot v, I'll take their corresponding components. The first one for u was 0, first one for v was 0, so those I'm going to multiply. So I'll do 0 times 0. Then the second one for u was 0 also, and the second one for v was 2, so I'll multiply 0 and 2, and I'll add that to the last ones, which were 1 and 2, multiply those, and I get 0 plus 2 equals 2. Notice you get the same thing either way. That's how you know you have a good alternative definition. Let's calculate u dot v for the following vectors in R4. So what we'll do is we'll take the dot product the same way as we did in the previous part. We'll take -1 times -3, because those are the first components of u and v. We'll add that to 3 times -4, add that to 5 times 1, and add that to 7 times 0. And we'll get -4. How about we find the angle between a diagonal of a cube and one of its edges? Alright, so how about I try drawing a cube? And it's one face. Go up a little bit. Oops. Alright, that'll pass for a cube. And I'm going to put some axes in this guy. Let's see how I want to draw this. I'll put the z-axis over here. Put the x-axis over here. And I still need a y-axis. I'll put that over, oops, put that over here. Now, how about I make vectors along the edges that end up at the vertices of the cube. So I can call this one u1, I'll call this one u2, and I'll call this one u3. Notice the coordinates of u1 will just be some constant, let's say k, and then z and y will be 0 along the x-axis. For u2, it's a cube, so it'll have that same constant, but in the middle for the y value. And then for z, whatever constant it is will be the z value, depending on how big the cube is. Okay, now I want a diagonal of the cube. So how about I draw that? We can call that d. And there's some angle theta between u1 and d. That'll be the angle between diagonal and one of the edges. So I have to figure out what that is. Well, let's write what we have so far. u1 is the vector k0, 0. u2 is the vector 0, k0. And u3 is the vector 0, 0, k. Notice if k is how long it is along the side of the cube, then that means that the coordinates over here must be just 3k's. So those are the coordinates for d. So that's just u1 plus u2 plus u3. We can figure out the angle theta by figuring out what cosine theta is, because remember the dot product is equal to the length times cosine theta. So that means that cosine theta is equal to u1 dot d divided by the lengths of u1 and d. I need one more. There we go. And that's just going to be, let's see, dot product of u1 and d. Well, the zeros will kill off these guys, so we just have k times k is k squared. And in the denominator, we have the length of u1 is just the square root of k squared, so that's just k. And the length of d is k squared plus k squared plus k squared. That's 3k squared. Take the square root. So square root of 3k squared. Okay, the k squared will cancel with k squared in the bottom, because square root of k squared will be k, and we'll get 1 over square root of 3. So cosine theta is 1 over square root of 3. That means that theta is equal to cosine inverse of 1 over square root of 3, which is about 54.74 degrees. In the special case where u equals v in definition 3.2.4, we obtain the relationship v dot v equals v1 squared plus v2 squared, and so on through vn squared equals the length of v squared. So that shouldn't be too surprising, since if you take the dot product, you just take each component, multiply it, you get a v1 from v, a v1 from v, so you get v1 squared. Since the length is the square root of this thing, we just square it to get rid of the square root, and you get length squared. So that means we have a formula for expressing the length of a vector in terms of a dot product. The length is just the square root of a dot product. If u, v, and w are vectors in Rn, and if k is any scalar, then u dot v is v dot u. It should make sense the dot product is commutative because multiplication is commutative, and we're just multiplying each component that corresponds. The dot product distributes over addition. The dot product distributes over scalar multiplication. Ku dot v is ku dot v. And the dot product, just like lengths, are greater than or equal to 0 and only equal to 0 if we're taking the dot product of the 0 vector. Provided that you take the dot product of a vector with itself, that is. If u, v, and w are vectors in Rn, and if k is a scalar, then 0.v is v.0, which is just 0. Notice this is not the 0 vector, because remember when we take a dot product, we multiply components and we add them up. So we get the sum of a bunch of numbers is just a number, so it's a scalar. If we take u plus v and we dot it with w, that distributes 2. It's the same thing as u dot w plus v dot w. U dot v minus w is u dot v minus u dot w. Same thing with u minus v dotted with w. And k times u dot v is u dot kv for some scalar k. As an example, how about we calculate u minus 2v dotted with 3u plus 4v. So this thing is the same thing as saying u dotted with 3u plus 4v minus 2v. I'm separating out the u and the minus 2v, distributing in it. Minus 2v dotted with 3u plus 4v. And that thing is the same thing as 3 times u dot u plus 4 times u dot v minus 6 times v dot u minus 8 times v dot v. And that is equal to 3 times the length of u squared, because the dot product is the length squared, minus, let's see, u dot v, v dot u commute. So 4 will cancel with 4 in there. So I'll just get 2 left. And v dot v is length, so that's minus 8 times the length of v squared. Next up, we have the Cauchy-Schwartz inequality. If u is equal to u1 through un and v equals v1 through n are vectors in Rn, then u dot v is less than or equal to the length of u times the length of v. So that's kind of cool. If u, v, and w are vectors in Rn, then this leads us to the triangle inequality. U plus v will be less than or equal to the length of u plus the length of v. Also gives us that the distance between u and v is less than or equal to the distance between u and w plus the distance between w and v for some other vector w. So let's prove A really quick. If we have the length of u plus v squared, then we can write that as the dot product of u plus v with u plus v, but then we can distribute and get that that's u dot u plus 2 u dot v plus v dot v. So u dot u is just length of u squared, v dot v is length of v squared, and u dot v will be less than or equal to the absolute value of u dot v. And then Cauchy-Schwarz comes in and tells us that that absolute value is less than or equal to the lengths multiplied. So then we could just kind of undistribute, or however you want to think about it, and get that this is the same thing as the length of u plus the length of v squared. Let's prove the second one now. The distance between u and v is the length of u minus v, which is the same thing as the length of u minus w plus the w minus v. This is a trick where we just threw in minus w plus w. It's the same thing as adding 0 in between. So then this thing by a is less than or equal to the length of u minus w plus w minus v, which is just the distance between u and w and v. So that gives us a parallelogram equation for vectors. If u and v are vectors in Rn, then length of u plus v squared plus length of u minus v squared is equal to 2 times the length of u squared plus length of v squared. And we can prove that pretty quick. We just take u plus v squared, make it the dot product. Take u minus v squared, make that the dot product. And then just multiply out and rearrange terms. We get a ton of cancellation. It just ends up becoming 2 times u dot u plus 2 times v dot v. So that's just 2 times the length of u squared plus the length of v squared. If u and v are vectors in Rn with the Euclidean inner product, then u dot v is 1/4 of the length of u plus v squared minus 1/4 of the length of u minus v squared. Again, we just take u plus v squared, write it as a dot product, and then expand. Take u minus v squared, write it as a dot product, and expand. Then just take 1/4 of this guy minus 1/4 of this guy, and notice you're gonna cancel out pretty much everything except for 4 of this. Well, you take the 1/4 and then it just becomes this, u dot v. If A is an n by n matrix and u and v are n by 1 matrices, then AU dot v is u dot A transpose v, and u dot AV is A transpose u dot v. This shouldn't be too surprising, because if you have, say, just u and v n by 1 matrices, and that means that they look something like this, with like little column matrices, then if you were to take u dotted with v, then you're just taking all of the entries over here and multiplying them, well, maybe a star is better, multiplying them by the corresponding entries over here, but you can't do that super easily because they're both column vectors. So what you have to do is first transpose u and then multiply it by v, and then you can do matrix multiplication to get this entry times this entry, same as the dot product. So all this does is it just throws an extra matrix in there. It follows by just properties of the dot product and transpose, and that's pretty much it. Let's suppose that A is this matrix over here, U is this column matrix, and V is this column matrix. How about we verify that AU dot V is U dot ATV just in this case? So let's take A times U. So that's 1 minus 2, 3, 2, 4, 1, negative 1, 0, 1. And I'm multiplying that by minus 1, 2, 4. You should get 7, 10, 5. Okay, how about I take A transpose times V? Well, if I transpose, I get 1 minus 2, 3. First column is my first row from A. And then I'll get 2, 4, 1, and 3. No, sorry, got ahead of myself. I was copying that column. Minus 1, 0, 1. And I'll multiply that by minus 2, 0, 5. That'll give me negative 7, 4, negative 1. Okay, so now let's take A U dot V. So that's 7 times minus 2 plus 10 times 0 plus 5 times 5. And that's just 11. If I want to do now U dotted with A transpose V, then that's minus 1 times minus 7 plus 2 times 4 plus 4 times minus 1, which is also 11.